So in last lecture we discussed about how to write the structure model of a 3-bit adder. Now in this lecture I will explain about the test bench of this 3-bit full adder and the software demonstration of this. So here this is the structure model of 3-bit parallel adder, and this is the test bench diagram. Here unit under test is the parallel 3-bit adder, and uh, the ports of the test bench, the name I have selected exactly same as the names of the parallel adder, like A0, A1, A2, B0, B1, B2 and C1. These ports of test bench are connected to the ports of input ports of uh, parallel adder, and they must be declared as a rig type in the test bench. The ports of the test bench which are connected with the output ports of unit under test should be declared as wire type. Okay, so here this is a test bench. So name of the test bench is test bench itself, and here you see rig A0, rig A1, rig A2, rig B0, rig B1, rig B2, rig Cin. These are the ports of test bench which are connected to the input ports of unit under test, and wire S0, wire S1, wire S2, wire Cout are the ports of test bench which are connected to the output port of unit under test. Then in next line, parallel underscore adder is the name of unit under test, and the instantiation is given here. Dot A0 is associated with A0. Dot A1 of unit under test is associated with A1 of test bench. Dot A2 is associated with A2 of the test bench. B0 of unit under test is attached with the B0 of test bench. So in this way we have done the instantiation. Now we will use the initial keyword because this test bench has to be executed once. So whatever we will write inside initial, that will execute only once. Now since there are more than one statements inside the initial block, that's why they have to be enclosed in between begin and end. Okay. Then $monitor is the directive of the test bench which is used to to run the simulation whenever the variables of the test bench are getting any whenever there is change in the value of the variables of test bench. Means these are the variables A0, A1, A2, B0, B1, B2, Cin, S0, S2, S1, Cout. And here these variables are declared as bit type. So you see here A0 is equal to percentage B. B means bit type. All these variables are bit type. Now in statement number 1, the value of, so see basically here how this addition will be done. It will be done in this way: A2, A1 and A0. This is the first 3-bit number. This will be added with second 3-bit number which is B2, B1 and B0. So this addition will be performed and we will get S0, S1, S2 and final Cout. So in statement 1 A naught is 0, A1 is 0, A2 is 1. B naught is 0, B1 is 1, B2 is 1. So in this case the result will be result will be, I will write here 0, 0, 1 will be added with 0, 1, 1. So result will be 1 plus 1 is 0, carry 1 plus 1 is 0, 1, 0, 0. So in this case the result will be 1, 0, 0. Now in statement number 2, A naught is 1, A1 is 0, A2 is 1. One minute. In statement number 1, one number A naught is 1. So here I did this mistake here. Here this is 1. So in first case A naught is 0. A naught is 0. Okay. A2 is 1. A2 is 1. So this is A2. This should be 1. This is 1. So if we add this, then we are getting 1, 1, 1. This is the result. Okay. Here it is 1, 1, 1. And final C out is 0. Right. Okay, I will write C out also here as there is in the result C out. So in the second statement A naught is 1. Okay, here A naught is 1. So here in the stimulus of the second number is 1, 0, 1. 1, 0, 1. Right? This is A naught. And for second number B naught is 1, B1 is 1, 1, 1, 1. These are 1, 1, 1. So result of the addition is 1 plus 1, 0, 1 plus 1, 0, 1 plus 1 plus 1 is 1 and final carry. So result of the second will be 1, 1, 0, 0. Right? Okay. So in this way these results will be generated as per these stimulus, as per these inputs, right, in the test bench. So I will show you the demonstration. Okay, I will start with a new project. I will give the name of the project as adder. Then I will give the path of my demonstration folder in my desktop. So desktop demonstration. Okay. Right. Now I will create the source file, Verilog module parallel underscore adder. Okay. So this is the structure model of parallel adder. I will paste this code here. Okay, I will save this. So the moment I save this, here you can find three components has been created. F naught dash full underscore adder, and then there is a bracket. In bracket nothing is here. In all the three components you see F1 dash full underscore adder and bracket, and F2 full underscore adder and bracket. In bracket nothing is here right now, because we have to write the either structure model or behavior model or data flow model of this component full underscore adder. Then you find in this bracket that particular file will be added. So what I will do, I will take that code of structure model of full underscore adder. I will take this. Okay, now I will create another source file here in the same project. In the same project, Verilog module full underscore adder. Okay. Now you see here full f naught full underscore adder, and within bracket you can see the source file full underscore adder dot v. Same way in all the three components this file is added. Okay, right. Now I will create the test bench. So for the test bench we will select Verilog test fixer. Name of the test bench is test bench. Next, I will take the test bench. Right. Now I will select this. I will select the simulation part, and in the simulation part, if I have selected simulation, you can find here test bench is there. This test bench is attached to UUT. Its name is full underscore adder, and it has three components F naught, F1 and F2. So for the simulation, select the test bench, and by default now this simulation is selected here, and I simulator. Check the behavioral syntax now. First we will check the behavioral syntax. It is okay. Now I will simulate this test bench. Okay, so this is the resultant waveforms. So now here you can see here in first case. First S0 is the first waveform, then below this S1, below this S2, below this C2, then A0, A1, A2, B0, B1, B2. These values are there. So what is our first values in the test bench? A0 first is A0 is 0, A1 is 0, A2 is 1. B0 is 0, B1 is 1, B2 is 1. So you check here. A0 0, A1 0, A2 1, B0 0, B1 1, C2 1. So if we add these, then what result we got? Cout is 0 and S0, S1, S2 will be 1, 1, 1. So we'll check in the output. 1 minute. 0, 1, 0, 0, and here it is 1, 1, 0. Okay, 1, 0, 0, 1, 1, 0. So basically it is, or here itself you can find A naught is 0 and B naught is 0. So 0 plus 0 is 0. So S0 should be 0. So you check here, S0 is 0. A1 is 0, B1 is 1. So if you add these two numbers, result will be 1. Means S1 is 1. So see here, S1 is 1. Now A2 is 1, B2 is 1. So if you add A2 and B2, both are 1. So result will be 0 and carry out is generated. So S2 is 0, S2 is 0 and carry out is 1. So you can check this is working. Now the second stimulus, if you check, the values of A0 is 1, A1 is 0, A2 is 1, B0 is 1, B1 is 1, B2 is 1. So if you add these, so what will the result? A0 is 1, B0 is 1, 1 plus 1 is 0, carry is 1. So S0 is 0, okay. Then A1 is 0, B1 is 1 and previous carry was 1. So 1 plus 0 plus 1 is 0 and another carry is generated. So S1 is 0. See, S1 is 0 and another one carry is generated which will be used in the addition of MSB. So that one A2 is 1, B2 is 1. So A2 is 1, B2 is 1 and previous carry was 1. So if you add these 1, 1, 1, the result will be 1 and final carry out. So S2 is 1. So you check here, S2 is 1 and final C out is generated. So in this way you can verify all these waveforms. It is giving us the functionality of parallel adder, 3-bit parallel adder. Okay, now what I will do, I will implement this design. So I will select this parallel adder and I will run the synthesis tool. Okay, synthesis is completed. And if you check the RTL schematic, then if you check this RTL schematic, so see, this is the block diagram of the 3-bit full adder. So A0, A1, A2, B0, B1, B2 and Cin are the inputs and outputs are S0, S1, S2 and C out. Double click this block, then you see how we have done the interconnection. In that way it is showing here. See this F0. Then this is another full adder F1. This is another full adder F2, right? And in this way it is interconnected. So this interconnection is there. See F0. This is carry out. This wire carry out. It is connected to the carry in of F1. Now here in F1, the carry out this wire is connected to the C in of F2. So exactly same way how we have done, how we have written the structure model code, exactly same way you find this structure. Now in this full adder F0, if you double click this, so internally it is implemented in this way, right? Internally it is implemented in this way. Okay. And if you see the technology schematic, then in terms of lookup table, you will find this structure. You double click this and you check. See, and now these are the lookup tables. One lookup table is here, it is implementing this logic. Another lookup table is here, it is implementing this logic. Another lookup table is here, it is implementing this logic. Another lookup table is here, it is implementing this logic. This is another lookup table and this is another lookup table. So to implement this logic, 1, 2, 3, 4, 5, 6. 6 lookup tables are required. So in this way you have to do you have to run this simulation by using the test bench.